Today we start Newton's laws, which is sort of the fundamental topic of classical mechanics and of this course. And we'll take it in two parts. So in this part, we'll talk about qualitative description of the laws and the observational evidence that sort of backs up these assumptions that we make. In part two, we'll talk about the precise formulation of the law, the precise statement of each law, and then we'll do some examples. And then we'll continue with Newton's second law in particular after that, because that's going to be our primary thing for solving problems. But first we do sort of a qualitative look. We'll talk about how Newton's laws are an axiomatic theory, and we'll talk about what that means. We'll talk about the evidence for each law, and in the third that we'll discuss, which is actually called Newton's first law, we'll define something called inertial frames, which is an important definition within the laws that tells you when you're allowed to apply the other two laws, when these actually work. And then we'll end with just a couple notes about what you can do with Newton's laws. So I want to talk generally for a moment about what the set of Newton's laws does for us. And we have started the semester by talking about kinematics, and that means that we've talked about the position vector, the velocity vector, the acceleration vector, and that gives us everything we need to precisely describe how things move. Dynamics is the subject of Newton's laws, and that tells us why things move the way they do. So while you can describe in kinematics exactly where something is moving through space, dynamics tells you why it's moving in that particular path. And it's the connection between something called forces on objects and their kinematic motion. So we had to describe kinematics first. In fact, Newton invented calculus in order to write down the dynamical laws. But now Newton's three laws of motion will give us everything we need for the field of what's called classical mechanics, the motion of objects. So we say that Newton's laws are an axiomatic theory, and let's just talk for a moment about what that means. You might have heard of axiomatic theories or axioms in mathematics, like for geometry, there are these rules about parallel lines or intersecting lines or triangles. And basically you come up with a few simple rules, which then you can use to understand everything about the theory, to prove other things. So in particular, an axiomatic theory means that the laws that we write down, or the axioms, are the minimal set of rules needed to describe all phenomena. So these rules are not going to be redundant. You can't prove one from another, and you're not going to ever need any other rule. So everything should come directly out of Newton's laws. We're not going to take new laws out of our pocket when we come up against a new phenomena. So this will be it. We write down these laws and everything should follow from there. Another thing that you should say about an axiomatic theory is that you can't prove the laws. You can't prove the axioms. They're just assumptions that we make where everything else follows. So we're going to write down these statements, and we're going to try and be careful here to show that they make sense based on what is observed in nature. So they can't be proven, but they should agree with what we see in our observations of nature. And maybe it's helpful to think about a couple other axiomatic theories that you might be more familiar with. So one is evolution, Darwin's theory. So what are the axioms there? Well, there's a few simple rules that lead to everything that we know about life. So this is not my field, but every organism has some traits. Maybe that trait is like an opposable thumb. These traits can then be passed on to their descendants, to their children, through the process of reproduction. However, the process of reproduction is not perfect, and so sometimes there are mistakes that are made. If you've watched the TV show Westworld, Anthony Hopkins' character talks about how all of life came from one simple tool, the mistake. So it's important that the process of reproduction doesn't give the traits exactly to the children, but there are every once in a while mistakes made so that you get some diversity among the children. And then Darwin's rule basically is that there's going to be some pressure from the environment that will allow some organisms to perform better than others, depending on how they, the random trait that they happen to have. So maybe one bird has a longer beak than another bird, and they're able to get the bugs better out of the tree. And you get this process called natural selection, where those with the longer beaks survive and those without the longer beaks do not survive, and eventually birds have longer beaks, those birds that need to get the bugs. So it's just a few simple rules: traits, reproduction, mistakes in reproduction, and then natural selection. And that leads to everything that we know about life. It leads to crazy things like mammals that evolved into land-dwelling creatures, but then somehow returned into the ocean to become whales. Things like these little bones in your ear that manipulate a little vibrating membrane that allow you to hear the brain. I mean, these are amazing things. I guess one other axiom that goes into this is the extraordinarily long timescales over which this can happen. These mistakes can accumulate, this natural selection can happen. But it's just a few rules. Another is the central dogma of biology. So we know now that traits are passed on through the genome, through DNA in many organisms. And then DNA is then, genes of the DNA are then transcribed into little RNA copies, which are then translated into proteins. And that basically is how an organism sort of creates its structures. And so just knowing these simple rules allow you to sort of understand exactly how an organism can build itself. With the vaccine for COVID-19, once they had the genome, all they had to do was simply basically type that into a computer, and they could create the genome that would make the mRNA vaccine that we use now. So those are some examples of axiomatic theories. Simple set of rules from which very complicated things can arise. So let's start with perhaps the most famous of Newton's laws, Newton's second law. This is, as we'll see, F is equal to ma, but we'll make it a little bit more precise. So before we talk about what Newton's second law is, let's talk about what it's not. Before Newton, so as I said before, Newton came around in the 1700s, or maybe I didn't say that, but Newton came around in the 1700s. Aristotle's laws were what were assumed prior to Newton, and Aristotle was from back in 350 BC. So Aristotle had a view of nature which said that objects tended to their natural state. So rocks fall to the ground. It's sort of obvious that rocks will fall to the ground because that's where all the rocks are. Air, I guess, floats to the sky. And the celestial objects, so stars and planets and whatever it is that they're seeing moving around in the sky, these sort of travel on spheres. So these sort of rules that come from just sort of a general observation of the world around us are what Aristotle used to develop his natural theory. One thing that sort of solidified his theory was bubbles. So if you look at bubbles in water, you see that the bubbles float to the sky. So it really solidifies the theory about air going to its natural place, its natural state. So what does this mean about objects and their motion? Well, he said that objects tend to be at rest. That's the natural state of objects. And that forces are required, so interactions are required for those objects to have motion. And this was accepted, and in fact, it's very intuitive. So one might write Aristotle's law of motion that forces, which are just interactions on objects, are proportional to velocity. So if you want to get a velocity of an object, you have to apply a force to that object. And so people accepted this, and it's even intuitive to us now. I mean, if you're riding on a skateboard, then you know you have to push off the ground. You have to push repeatedly in order to keep going. So in order to have some velocity here, you need to apply forces to make yourself go. Forces cause you to go. If you're driving in a car, you can't just get into your car and press the gas pedal down once. You have to keep your foot on the gas. So keep up the gas. If you don't keep up the gas, then your car will stop. It tends to its natural state, which is at rest. So Aristotle's theory is a fairly intuitive one. It seems to agree with what we see in the world. But of course, it's wrong. It's wrong. So maybe we should cross out this whole page just to be clear. Aristotle's theory is not correct. We're going to talk about what the correct theory is. Even though it seems from our observations that we need forces to cause velocities, it turns out not to be true. So what is true? Well, in the middle of the second millennium, there were a number of people who made careful observations of astronomical objects like the orbits of planets around the sun, and of just objects on Earth like Galileo's dropping of balls or rolling balls down the hills. And Kepler in particular took some careful data to map out the orbits of moons around planets. And all of that led to Newton's reformulation of the law of motion, which can be stated as forces cause changes in velocity. So you could also say that the natural state of an object then is a constant velocity. That might be at rest, agreeing with Aristotle's theory, but it might also be with some constant velocity relative to the road. So the natural state of an object is just to move with a constant velocity, and then interactions, these forces, are what cause those velocities to change. So what does that mean in terms of kinematics, what we've talked about already? Well, it says that a force then should be proportional to the acceleration of an object. Remember, the acceleration is something like the change in velocity over the change in time, so we see that forces cause changes in velocity. So that was Newton's idea. So let's take a look and see if this makes sense, despite the fact that we seem to be okay with Aristotle's idea. And we'll do it in a situation where friction and air resistance are minimized. And friction and air resistance are really the reason why Aristotle's theory seemed to make sense. And we'll come back to that in a moment. But if you're ice skating, you have these sharp blades on ice, and there's very little friction, so we don't have to worry as much about friction. So let's imagine a couple of scenarios on the ice skating rink. So let's say you first start out, and you're the ice skater, and so here are your ice skates. And you start out by pushing on the wall. So there you are. I should give you a hat. You push against that wall, and that means that there's going to be a force on you which points away from the wall. So what does that mean in terms of your kinematics, in terms of your velocity? Well, you started with an initial velocity of 0, just standing next to the wall, but then at some moment later, you will have a final velocity which is non-zero. So you go from an initial velocity of 0 to a final velocity which is rightward. How do we explain this with Newton's idea? Well, it says that forces should be proportional to the acceleration, or to the change in velocity. What's the change in velocity here? Well, we could write it. Delta v is equal to v final minus v initial. So what does that look like on a coordinate system? We can just do that graphically. Well, v final plus the minus v initial vector is just going to be v final plus 0, which means that our resultant is exactly the same as v final. So delta v points in that direction. So this makes sense based on Newton's law. The force is proportional to the change in the velocity vector. The force pointed right, and therefore the velocity changed toward the right, causing you to move from rest to a rightward velocity. So what about once you're moving freely? So I guess I can just copy you there. I don't know what happened to your hat. I guess you gave yourself such a force that your hat fell off. So here you are, moving freely across the ice. And at this point, there are no forces on you. There's no interaction with any other objects. So what does that mean? It means that you are going to be, in the next moment, looking exactly the same. So I should write this as v initial looks like this, and v final looks like this. And what is delta v? Well, delta v is equal to v final minus v initial, which is equal to 0. No forces leads to no change in the velocity. So again, this agrees with Newton's law. And finally, you arrive at the other side. So let's draw you over there. Maybe somebody gave you your hat back. Or maybe it's a new hat. You arrive over here, and when you do, you grasp the wall to stop yourself. So in that case, there's going to be a force on you which is backwards. So we have a backwards force because you're hitting the wall. You had an initial velocity before you hit the wall, based on this picture here. So here you are with your initial velocity. And then your final velocity was equal to 0. You were stopped by the force. So does that make sense with Newton's second law? Well, the delta v is v final minus v initial, but v final is equal to 0, so it's just the minus v initial vector. Well, the minus v initial vector is this vector, but pointing in the opposite direction. So again, the delta v vector will point in the same direction as the force. So forces cause changes in velocity. And we can see this very clearly as long as we're allowed to ignore friction and air resistance. So that was sort of one-dimensional look at Newton's second law, but we could also do it two-dimensionally. So let's say that you started out over here next to the wall, and then now we're looking down on you. So like here's your hat, and then I'll just amplify your ice skates here. So these are your ice skates. So there you are, skating across. Maybe this is your trajectory here. Your initial velocity vector at this moment is going to look like this. So that's v initial. And then let's say at some moment you decide to push off, maybe with your right foot. So here you are. Here's your left foot that's sort of staying the same, but you push off with your right foot. There's your leg pushing off with your right foot. So what does that do? Well, that's going to cause a force on you like this. So you're actually pushing on the ice in the opposite direction, but that's a force on the ice. And because of that force, you'll get a force on you. That's actually another one of Newton's laws that we'll come to in a moment. Forget about that for now. There is a force on you that's going to point in the direction I've drawn it. So what does that mean? Well, we have delta v is in the same direction as the force. That's our assumption from Newton's second law. So delta v, which is equal to v final minus v initial, I could find v final. So v final is v initial plus delta v, and then I can draw it. So we had an initial vector that looked like this. We have a delta v that we're going to add to it. which looks like the direction of the force, something like this. And therefore, the final velocity vector, the resultant in that equation I've written down, is going to look like that. So that means that your velocity vector went from along this path here to something more like this, B final. So the force caused a change in the velocity. I guess I should, sorry, it's not quite that, right? Oops. Oh, geez, I can't. So the final velocity is not horizontal like the force, but the final velocity is more sort of angled. It's somewhere in between the horizontal and the force. Should have tried to make it more dramatic. But now you're moving at an angle with respect to your original direction, and that's because of the delta V that was caused in the direction of the force. So what I'm trying to show here is that Newton's second law is a vector equation. The change in the velocity should be proportional to the force, meaning that it's in the same direction as the force. And you can think about this exactly as a vector effect. So a velocity vector that pointed in this direction is affected by a delta V that points in the direction of the force, and that causes a new velocity vector which is slightly angled with respect to the first one. Doesn't mean that your new velocity is exactly along the force direction, it just makes a little change there. Okay, so what can we say? Well, I think we've already said all of this. Newton's second law basically says the force is proportional to acceleration. Our definition of acceleration, at least the average acceleration, is delta V over delta T, so the force is proportional to the change in velocity. And then we've used that to show how the rule, remember this is just an assumption, actually matches what we see in the world. So that brings us to the question, why do we have this nice intuition for Aristotle's view of physics, this idea that we tend to a natural state of rest? Well, if you look at the ice skater over a longer period of time, what you'll see is that they start out with some initial velocity that looks like this, but over time they start to slow down, and so at some later time they might look like this. I don't know what's going on with their arms. And their velocity is going to be smaller. V final is smaller. So the delta V for this thing that you would observe is V final minus V initial. Well, what is that going to be? It's going to be this small vector added to the opposite of the large initial vector, V final, V initial. So delta V is going to point backwards. So for an object that's just moving across the ice, in reality they will slow down, and that means that the delta V vector points backwards, which means the acceleration points backwards, which means we could draw that here. The acceleration vector must be pointing backwards, which means that there should be a force pointing backwards. That's what Newton's second law requires. And in fact, there is a force. It's called the frictional force. So there's a force acting on those skates, which is dragging the person backwards in some sense. It's an interaction between the ice. In fact, there's another force as well. So unless you're ice skating in a vacuum, which is not generally a good idea, then there's some air blowing against you. You can feel that when you're ice skating. And so there's a force of air resistance pointing backwards. So there are multiple forces acting on the person, which is causing a net force, the sum of these forces, to point backwards. And therefore, we get an acceleration that points backwards, and what that means is the velocity becomes smaller in magnitude, that the object slows down. So that's why Aristotle's physics seems to make sense. Objects tend to their natural state. But if you notice, my entire explanation here was from Newton's second law. So Newton's second law, in fact, explains why we normally see objects slowing down. It's because of frictional forces that cause deceleration, changes in the velocity to make it slower. Okay, we'll move on to the next law. So we did Newton's second law. We're going to do Newton's third law now, and then later Newton's first law. So Newton's third law, I've heard some people say, well, this is just sort of obvious. And then I've heard other people say that this doesn't make any sense. Why is this true? So I'm not sure what your opinion of it will be. We should check in afterwards. But it turns out that we need this law in order to extend the description of motion from the motion of one particle to the interaction of multiple particles. So Newton's second law was a law that described the motion of just a single object, and now we're going to talk explicitly about multiple objects. So let's look at the ice skater again. And I sort of went through this very quickly. I said you pushed off the wall if you're the ice skater. So you're pushing off the wall like this. And we said that there's a force on you because of that push. That's what caused you to accelerate, and that's what caused your velocity to go from 0 to a rightward velocity. Well, let's give that force a little bit more precise name. We'll call that the force of the wall on you. So that's a force of the wall on you, and it's a force that you get because your hand is touching the wall right there. So you're touching the wall, and therefore the wall is pushing on you. What Newton's third law says is that in any interaction between two objects, there's a pair of forces on the two objects. So if there's a force of the wall on you, then there must be what's called an action-reaction pair, which is the force of you on the wall. And what Newton's third law says is that those forces are equal in magnitude but opposite in direction. Or you could say it more simply, those forces are opposites of one another. So when we say you pushed off the wall, or the skater pushed off the wall, what we mean is you pushed on the wall, you caused a force of you on the wall, and because of Newton's third law, there was an equal magnitude force of the wall on you. And that's the thing that caused you to move to the right. So let's write this down. It says, in any interaction between object A and object B, the force of A on B is opposite to the force of B on A. And what we can say there in equations is B on A, I guess I said it the other way around, A on B is equal to minus B on A. And if you take the magnitude of that equation, then you'll find that their magnitudes are equal because the minus sign goes away. And what the minus sign means, as you know from vectors, is that the AB vector is exactly in the opposite direction of the BA vector, the force of B on A. So that's the rule, and you can see that there's some evidence for it. When you push on the wall, you get a push in the opposite direction. And people from Newton onwards have tested to see how those two forces compare, and it turns out that they are exactly the same strength. So why is it non-intuitive? Well, let's try and look at some examples. So if you have like two pool balls running into each other, then the moment that they hit, you should get, if we call this like ball A and ball B, you'll get a force of ball A on ball B, and it will point like that. But you should also get a force of ball B on ball A. And that's despite the fact that maybe ball A had some initial velocity, but ball B had an initial velocity of 0. So maybe you would think, well, if ball A comes in with some velocity and ball B is motionless, then B will get a bigger force than A. Turns out that's not true. The forces in any interaction are exactly equal. we could make it even more dramatic. We could say, well, I'm going to take a bowling ball and send it down the road, and then I'm going to put a ping pong ball on a little pedestal here. Bowling ball rolls into the ping pong ball, and you might think, well, the force of the bowling ball on the ping pong ball should be much larger than the force of the ping pong ball on the bowling ball. But in fact, it turns out that that's not true. The force of the bowling ball on the ping pong ball is exactly the same magnitude as the force of the ping pong ball on the bowling ball. They're opposite in direction, but equal in magnitude. So in some sense, we just have to accept that. I mentioned at the very beginning that you can't prove these rules. You just have to write them down, see that they agree with nature. And so once we agree that this rule agrees with nature, we just have to use it. We have to accept it. And that will lead to everything else. It'll lead to the description of the motion of multiple objects, like planets going around suns. It will lead to many particle systems, like gases and fluids. All of it comes out of Newton's third law. So we arrive at our last law, which is called Newton's first law. I left it to last because it's sort of the least intuitive of the laws and probably the most misunderstood. So you're not going to see the way that I describe it here in your textbook. I think that the way that people often talk about Newton's first law is a little bit confusing or wrong. So you might have heard the way Newton's first law is described is an object in motion tends to stay in motion, an object at rest tends to stay at rest. There's some truth to that, but usually it's misinterpreted. So I want to go through carefully what Newton's first law is, and the way that we have to talk about Newton's first law is to define something called inertial frames. So this is very non-intuitive, and it's something you're going to have to do a little bit of work to understand. And I'll try to give you some examples that make it make sense. So the reason for Newton's first law, remember, we have an axiomatic theory, so each of the axioms is necessary to describe the theory. The reason that Newton's first law is necessary is because it turns out that Newton's second law and third law don't work all the time. There are specific circumstances where they don't work, or a better way of saying that is that they work only in specific circumstances, which are called inertial frames. So we need to have a way of defining what those circumstances are, defining the inertial frame, and then stating that you can only use Newton 2 and 3 when you are in an inertial frame. That's what Newton's first law is. So let's look at this example. So you're sitting at a table, maybe with a Coke can in front of you here. So here's your Coke. It should be red, I guess. I'm getting paid here by the Coke company. And you're about to drink your Coke, right? But you're sitting at a table and it's inside of your RV, your recreational vehicle. You're taking a trip, I don't know, out to Colorado or something, and your friend is driving. And all of a sudden, the Coke can, well, let's actually describe it just from your perspective. So I'm going to take you, and I'm going to draw you outside here, just in your little box. So here you are. This is your perspective. So you're inside of an RV, all the blinds are closed, so you only really see what's going on right here. And let's say, all of a sudden, the Coke can goes from having an initial velocity of 0 to suddenly moving towards you, putting yourself in danger of getting Coke all over you. So, why did this happen? Well, we have rules for motion now. We have Newton's second law that tells us if there's a change in the velocity from 0 to rightward, then we should be able to describe that by a force. There should be a force that's pushing the Coke can towards you. But very obviously, there is no force. You know, there's no wall, there's no second person pushing on it. Friction will move opposite to the motion of an object. It shouldn't be able to suddenly make a can go forward. So it seems like there's a violation of Newton's second law here. You have an object that accelerates without any force to describe that acceleration, to cause that acceleration. So this is a bad situation. It seems like our rules of nature suddenly don't work because we're sitting inside of an RV. So why is that happening? Well, the reason that that's happening is because if you look outside, the RV itself had some initial velocity, which was forward, but then maybe, I don't know, there was a deer that came by, and therefore your friend put their foot on the brake and caused an acceleration which slowed down the RV. The final velocity is smaller. So what exactly causes that acceleration? Well, we can describe it with Newton's second law. There would be a force on the tires due to the road. That's usually a frictional force, which causes that RV to slow down. So Newton's second law, the force of friction against the car causes an acceleration in the same direction, opposite to the velocity, so you slow down the RV. Well, what's happening to the Coke can? Well, maybe there isn't much friction between the Coke can and the table, and therefore the initial velocity of the Coke can, which from the perspective of the road was exactly the same as the initial velocity of the RV, right? If the RV is going 55 miles an hour down the road, then the Coke can is also going 55 miles an hour down the road. If the RV suddenly starts to slow down and the Coke can is not well attached to the RV, then the Coke can will continue to move at 55 miles an hour while the rest of the RV starts going slower, and therefore the Coke can moves towards you. If you can't see the outside perspective, then all you see is a Coke can moving towards you. You don't see that slowing down part. So what Newton's first law says is that we cannot do physics. We can't use Newton's second law and Newton's third law in a situation like the one inside the box here, the one inside the RV. So I've written it down here. Basically what it says is, first it gives you a definition of an inertial frame. So it says an inertial frame is one in which an object that experiences no net force moves with a constant velocity. That's the definition of an inertial frame. And in fact, it gives you, within the definition, an experimental test of whether you're sitting in an inertial frame. Because what it says is, if you look at all the objects around you, if they have no force on them, then they should be moving with a constant velocity. One example of a constant velocity is zero velocity. So if you're sitting at a table and you have a bunch of stuff on that table, it all has a zero velocity, you should expect those velocities to stay the same. Everything should stay on that table. If you suddenly see something move across the table, then that means you're not in an inertial frame. So it's a definition of an inertial frame, but also an experimental test of an inertial frame. So let's look at what that means for our picture here. This person is sitting in some room, which we could call a frame. They have a Coke can in front of them on which there's no net force. So there's nothing pushing on it to the side here. And yet, that object started to move. It went from a zero velocity to a rightward velocity. That object tells you that you're not in an inertial frame, because an object with zero net force did not have a constant velocity. So that's what an inertial frame is. And then the second part of Newton's first law says Newton's second law and third law should only be applied in an inertial frame. So we know what an inertial frame is now. We know how to test for it. You just put your object down on the table and make sure that it doesn't move on its own. If that's the case, then you can use Newton's second and third law. You can do physics. If it's not the case, then you can't do physics. So you, sitting inside the RV, are not allowed to use Newton's laws. That leads to a question: what do you do if you're there, sitting inside the RV? Well, what you have to do is you have to step outside the RV and find yourself an inertial frame, and that's what I described in this picture here, where if you step outside the RV, if you, the experimenter, or maybe your friend is sitting out here as an experimenter, they place a ball on the ground and they see that that ball does not move on its own, so they say, okay, good, I am in an inertial frame. The frame of the road is an inertial frame. Then they can start to do physics. Then they can say, okay, well, this RV had an initial velocity pointing to the right, the deer came in front, and so there was an acceleration backwards caused by a force of the road on the RV. That gave a smaller final velocity, and therefore the Coke can, which didn't have the same, it wasn't attached to the RV, so it just kept its same initial velocity. There were no forces on the Coke can, and therefore the initial velocity was the same as the final velocity. So while the RV starts slowing down, the Coke can just keeps moving on down the road. Okay, I said it was sort of non-intuitive, and from all that complicated explanation, you can see it's difficult to get a grasp on. You might want to look at that again, and we'll talk about it again in some other circumstances. We'll do a problem in the next lecture. So we have Newton's first law, second law, and third law. What can they give us? Well, let's just do a couple quick examples of what we get out of these laws. We've been talking about projectile motion. So if you have some object that's moving through the air, or I guess we were talking about free fall, so it's not moving through the air, it's moving through a vacuum. So it has some initial velocity, which points like this, but we know that it has an acceleration that points down. And I want to move this velocity vector off of it a little bit. So we're gonna draw the kinematic vectors off to the side. What Newton's second law says is that the sum of the forces on the object, which we call the net force, so we could write it in either of these two ways, are proportional to the acceleration of the object. And we call that proportionality constant the mass. So what's the case here? Well, if there's an acceleration downward, then that must mean that there's a force on the object also downward. And that force we call the force of gravity. So we can write that there's a force of gravity, the sum of all the forces on the object, which is equal to the mass times the acceleration of the object. We'll do an example next time that shows exactly what that gives us, but what we get out of Newton's second law is that we can explain the constant acceleration of all objects due to a force that is pulling them downward. So the reason that things move with an acceleration down is because everything experiences a downward force. We'll also be able to apply this to astronomical objects, like maybe the Earth and the Moon. It turns out that if the Moon, some planet, has an initial velocity vector that looks like this, and there is a force on the Moon, which is the gravitational attraction force of the Earth on the Moon, then the Moon will start to move like this. So moons move in elliptical orbits around planets, and we'll be able to describe that exactly. It all comes just out of Newton's first, second, and third laws. Everything we've talked about with Newton's second law so far has been the motion of one object, or we should say a particle. But you could take a bunch of particles and arrange them in some shape, maybe, and then you could connect them into a solid object, like a wheel, like this. If you look at the interaction forces between each of those particles, then you can start to develop the picture of how a solid object moves. You can talk about how it moves through space as one object. You can talk about how it rotates. We'll talk about that as an angular velocity. And so you can build up from the equation that represents the motion of a single particle into the motion of many particles, solid objects. This we call translational motion, and this we call rotational motion. And finally, you could think about many particles in a system each of them having their own velocities. And then when they interact, you're going to get, from Newton's third law, you're going to get action-reaction pairs, equal but oppositely pointed forces. So this is like force A on B, and this is force B on A. And because of that interaction, you can describe the motion of all of the particles in some box. And that will lead to the description of fluids and gases. So Newton's laws don't only describe particles, planets, and even solid objects, but they can describe very complicated systems like fluids. We won't make that connection precisely in this class, but we will talk about the motion of fluids, and it comes out of Newton's laws. So one last thing I want to say is that we're going to write down Newton's laws in the next lecture. We're going to use them to solve some problems, and they are really the only thing that we need to do the entire field of classical mechanics. That doesn't mean that we're only going to be doing Newton's laws for the rest of the semester. What we'll do is we'll use Newton's laws to develop some other concepts. So there's a concept of energy, which comes directly out of Newton's laws, and something called conservation of energy, which makes it easy to solve certain problems, and in fact becomes sort of an organizing principle for mechanics. You might have heard of the concept of conservation of energy. In physics, it's a very important concept. Another thing that we can develop is something called momentum, the momentum of particles, and that leads to a way of describing collisions between particles called the conservation of momentum. And then, as I mentioned above, we can talk about solid objects and their rotation. So we'll spend a week or so talking about the rotation of objects. But again, it all comes out of Newton's laws. So next time we'll talk about the precise statements of the laws. I've given you a little preview up here. This is the precise statement of Newton's second law. And then we'll do some examples with them. I'll see you then.